The last part of Module 6 covers elasticity. Welcome again to Engineering Physics. For bodies receiving load or force, deformation is a possibility. Deformation is the change of the object's size and shape due to load. There are three kinds of differential stress. First is tensional stress or extensional stress, which stretches the material, making the cross-sectional area smaller but length is longer. Second is compressional stress, which squeezes the material, making a shorter member with bigger cross-sectional area. And the third is shear stress. This will result in slippage and translation. Later on in Strength of Materials, you will learn stress in detail. This is the internal reaction of an object to an applied force. Mathematically, we can express stress as sigma is equal to F all over A, where sigma is stress, F is force, and A is the area involved in such stress. This area changes depending on which type of stress you are considering. Knowing that force is in newtons and area is square meters, the SI unit for stress is Newton per square meter, or what we call Pascal. Let's have some applications. A nylon string has a diameter of 5 mm and is pulled by a 150 Newton force. Determine the stress. The stress formula is given as sigma is equal to F all over A. Force is already given as 150 newtons, but area is a function of diameter. Thus, we use F all over pi all over 4d squared. By placing the values, we get 150 newtons all over pi all over 4 times 0.005 meter. That would be squared, which simplifies as 7,639,437.268 Pascal. Or that would be 7.639 megapascal. The next example says, what is the maximum force which a 20 mm bar can withstand without failure if allowable stress is 10 megapascal? 10 megapascal is a million of pascal, or can be converted into 10 Newton per square millimeter. And this is equal to F all over A, or F all over pi all over 4 times 20, that would be squared. Thus, solving for F, we get 3,141.593 newtons. Strain is the quantity which reflects deformation. The three types of strains are: linear strain uses epsilon, which is equal to change in length to the original length. Shear strain is denoted by gamma, which is equal to the change in x all over y. And lastly, bulk or volume strain uses theta, which is equal to the ratio of the change in volume to the original volume. Elasticity is the ability of a material to return to its original configuration after the applied load is removed. Take, for example, rubber bands. They return to their original configuration after the force is taken out. All materials have different rate of elasticity. Rubber is quite elastic compared to a steel bar, and the latter is even more elastic than concrete. Elasticity is also affected by creep and fatigue, as all materials can only carry a certain number of rounds of deforming and returning to their original state. All other terms you will learn in your higher courses. In 1660, an English scientist by the name of Robert Hooke discovered the relationship between deformation and the force applied. He stated that, for a relatively small deformation of an object, the displacement or deformation is directly proportional to the load. And mathematically, we can show it as force F is directly proportional to the deformation or change in size. Converting the expression to equality requires a certain constant, so the formula becomes F is equal to negative k delta x, where F is still force, delta x is deformation, and constant k is introduced in its negative sign to denote that the objects return to their original state. To illustrate, let's take a spring. The first image shows its equilibrium state, and upon the application of a certain weight mg, the spring will elongate at a certain x distance, and placing twice the weight will double the elongation too. Elastic modulus measures the resistance of the material to elastic or springy deformation. Low modulus materials are floppy and stretch a lot when they are pulled. squash down a lot when pushed. High modulus materials are opposite. They stretch very little when pulled and squash down very little when pushed. Floppy materials such as rubber are ideal for things like bungee jumping ropes, but would be catastrophic for something like the deck hangers of the Sydney Harbour Bridge. Like stress, there are three kinds of elastic moduli too. Young's modulus derives its symbol E from elasticity, which is French for elasticity. Shear modulus symbol of G comes from the French term meaning slipping, and that is glisma. The last is bulk or volume modulus, which is denoted as K, meaning compression, a German term for compression. Let's move on to Young's modulus, which, according to Britannica, is a measure of the ability of a material to withstand changes in length when under lengthwise tension or compression. It is sometimes referred to as the modulus of elasticity. Young's modulus is equal to the longitudinal stress divided by the strain. It is named after the 19th century British scientist Thomas Young, but the concept was developed in 1727 by Leonard Euler. Young's modulus is stated as the stress applied to the body is directly proportional to the strain induced on the body, which can be shown mathematically as sigma is directly proportional to epsilon. And making it in equality expression, we get sigma is equal to y epsilon, where sigma is stress, epsilon is strain, and y is Young's modulus. Let's attempt to expand the formula. So originally, we have sigma is equal to y epsilon, where sigma is force over area and epsilon is change in length over the original length. Placing both formulas in the equation, we get F all over A is equal to Y delta L all over L naught. So Young's modulus is then simplified as Y is equal to F L naught all over A delta L. Note that Hooke's law may also be stated in the same relation as Young's modulus, where the strain in a solid body is directly proportional to the applied stress within the elastic limit of the solid body. Let's have a basic example with this problem. A 5 mm diameter string has a length of 2 meters when a force of 200 newtons pulled it, making the length 2.02 meters. Determine A, stress, B, strain, and C, Young's modulus. A is stress, and we know it as force all over area. We can directly plug the given values into the equation as 200 newtons all over pi all over 4 times 5 millimeters squared. Then the answer comes out as 10.186 megapascal. Strain is deformation over original length, so that would be 2.02 less 2 all over 2, and epsilon is equal to 0.01. Take note that strain is unitless. From the two solved parameters, we can compute for Young's modulus as sigma is equal to y epsilon. So y is equal to 10.186 megapascal all over 0.01, and that is y is equal to 1018.6 megapascal. A stress-strain diagram denotes the elasticity of a material among others. From Hooke's law, we know that stress is proportional to strain, giving us a straight line until we reach the yield strength. Yield strength is the maximum capacity of a material where it can still return to its original size. After that, if there is still an increase in load or stress, the material can reach its maximum capacity, and that is what we call the ultimate strength. Load exceeding the ultimate strength can cause fracture or failure of the material. The area designated under the linear proportionality is known as the elastic region, and the value of the area is known as modulus of resistance. The other area under the diagram is known as plastic region. Plastic limit means that the material still attempts to return to its original configuration, although not entirely. Thus, this area, when computed, is known as the modulus of toughness. Check out discussion of Module 7, Oscillations.